Not recording.
Okay.
Okay, so hello everyone. It is my pleasure to have Tianfei Zhou with us today. He's a postdoctoral scholar in the computer vision lab at ETH Zurich. And before this, he was a researcher at the Inception Institute of Artificial Intelligence in Abu Dhabi, prior to which he obtained his PhD degree from the Beijing Laboratory of Intelligent Information Technology at the Beijing Institute of Technology. And his main research interests are around, computer vision, medical image analysis, and machine learning. And today, Tianfei will talk about his ICCV paper. I believe this was an oral presentation at ICCV on contrastive loss-based semantic segmentation. So we are looking forward to the talk, Tianfei, and you can start now. Thanks.
Okay. Thanks for the introduction, and also thanks for the effort to organize the seminar. Today I will talk about our recent paper, exploring cross-image pixel contrast for semantic segmentation. In this paper, we rethink the training paradigm that is widely used in current segmentation models and propose a novel training paradigm for based on contrastive learning. Although this is not a medical paper, I believe similar ideas can be also used to solve many medical image segmentation tasks. Oh, sorry. Semantic segmentation is a very fundamental task in computer vision and have received remarkable progress in recent years. Many recent studies focus on the image contact learning, which helps to capture the relationships or dependencies among pixels. Some methods like dilated convolution spatial pyramid pooling aggregate multiple pixels together. These techniques help the CNN to enlarge the receptive fields and improve the performance. In recent 2 years, transformer-based models have been popular. Some models also use self-attention to capture the very long-range relationships between image pixels. Some other works also design contact-aware optimization objectives, such as pixel affinity loss or IOU like Loa's loss. They directly verify segmentation structure during training to replace the pixel-wise cross-entropy loss. These methods explore pixel dependencies within individual images. They are able to well model the intra-image local contact. However, they ignore inter-image global contact across different images in the dataset. Let's see the figure in the right side. Both the two images include 3 categories: tree, car, and road. Let's take the tree class as an example. To segment the tree in one image, the current models often use the information in the corresponding image for segmentation. But can we use the information about the trees in other images as well to help the segmentation? This is promising because in this manner, for each image, we can use a massive number of contextual information existing in the dataset. But how can we do this? How can we model the relationships among different images or among different among image pixels? I think this can be done at least in 2 directions, which are very similar with the ideas used for intra-image contact learning. In the first direction, maybe we can use such as attention-based techniques to collect the information in other images and use the summarized information or feature to enhance the feature in the current image. It's very similar with the contact aggregation techniques. The second direction is to directly inject the relationship across different images into the training objective. In this paper, we focus on the second direction, but the first direction can also work well, and there are one ICCV paper for that idea. So let's see a more detailed example about the conceptual idea of the current segmentation model. Given a training mini batch, here are 3 images, we will project the image pixels into a joint segmentation embedding space using a FCN network or a transformer-based network. Based on the pixel embedding, we will use a segmentation head to perform pixel-wise classification. That is to classify each pixel into one particular category. So here the pixel embeddings are very important for a better segmentation. But what should a good segmentation embedding space look like? We think that it should at least meet 2 points. First, it should address the categorization ability of individual pixel embedding. That is, given a feature of one pixel, we are able to predict its correct label. This is actually the thing that the cross entropy loss is doing. Second, it should be well structured to address intra-class compactness and inter-class separation. However, this is mostly ignored in the literature. Motivated by the 2 points, we propose a new training paradigm for fully supervised semantic segmentation. As shown in the figure, the former part is exactly same to the standard pipeline. We use the FCN network to output initial pixel embeddings. Here we use different colors to denote the pixels of different categories. Then given the initial embeddings, we propose cross-image pixel contrast to produce a more structured embedding space. This is achieved by pulling close each pixel I by the black arrow to the pixels of the same class, and pushing far by the gray arrow to the pixels of different classes. This goal can be achieved by metric learning techniques. So let's first revisit the current popular unsupervised contrastive learning. As given in the equation, for each anchor point V, which can be regarded as a feature vector of an anchor image I, the information E loss is often used to distinguish a positive point V plus from a set of negative points V minus. The positive sample is often obtained from an augmented version of the anchor image. This criterion has been demonstrated successfully to learn invariant image representation. Compared with the other metric learning techniques, the inference E-loss can benefit a lot from a large number of negative samples to improve the performance. Okay, this figure provides an overall pipeline of current segmentation models. As shown in the figure, given 3 training images, we use the FCN network to project them into the embedding space. Then we will use a segmentation model to predict the segmentation scores. At last, cross entropy loss will be used to compare the segmentation score and the ground truth, and use the loss to guide the network learning. Here we can clearly see that the cross entropy loss is independently applied to each single image. Here the equation shows the standard cross entropy loss for a single pixel I. However, the cross entropy loss suffer two major limitations. The first one is it penalizes pixel prediction independently, but ignores the pixel relationships. The second is due to the use of softmax loss. The loss only depends on the relative relation among logits and cannot directly supervise on the representation. To address the limitations of the cross entropy loss, we propose a contrastive loss for segmentation. As shown in the figure, on the top of the standard pipeline, we introduce a projection head, as shown in the red box, to map the dense embedding of each image into a joint lower dimensional projection space. And we develop a fully supervised pixel contrastive loss as given in the equation to contrast the pixel embeddings in the projection space for embedding learning. Let's see the equation. Here, I is anchor pixel, and I plus is the positive sample of the anchor, which they have the same category. The I minus is a negative sample, which has different class label as the anchor and the positive sample. Then we will use the info NCE loss to do the contrast between the samples. Here, PI and NI denotes pixel embedding collections of the positive and negative samples. These positive and negative samples are, and as well as the anchor, are not restricted to being from a same image. In our implementation, we build a memory bank to collect and store historical pixel embeddings. Then the memory bank can be used in each mini batch during training.
Sorry, can I ask a question about that?
Okay.
So the input to fproj is the entire segmentation, predicted segmentation, right?
It's a projection head. It consists of two convolutional layers to map the embeddings into a lower dimensional feature.
And what is the input to the projection head?
The input is the embedding of the FCN network. It's a feature embedding.
So is that of the same size as the image?
Yes.
Okay. And then,
for example, it will project ResNet output with about 2048 dimensional feature into a 256 dimensional feature. Then
so
we
it's
will use the low dimensional feature to do the contrastive learning.
I see. So it is, for example, if it's a 2048 dimensional feature, okay, then that's not the same as the image size, right? So sorry, I'm a bit confused about the architecture.
The spatial size is the same, but the feature dimensional is different. Here we will maybe I know your problem. Here I and I plus is the pixel. We will do the pixel contrastive rather than the image level contrastive. Yeah, so we will sample from the features after the projection head.
So you will actually take, so I and I plus are
pixels.
Pixel values, I see.
Yes.
And that's the pixel values in the output of the projection head. Is that right?
Yes, yes.
Okay, thank you.
Okay.
Sorry, can I also ask a basic question?
Okay.
So Can you explain what are these circles which we see on the images? Sorry if I missed it, if you explained it already, but
Sorry. What's the question?
the circles which we see on the images, what do they represent?
The color of the circle. Okay, it actually represents
Not only the color, but what is that circle first, and then what does the color represent?
Okay, the circle it represents, it denotes the feature grid. You can regard it as a pixel, and the color denotes the pixels of different categories.
So each circle is a pixel, or?
Yeah.
I see. Okay. Thank you. Not like super pixel. It's just really an image pixel.
Actually, it will be a pixel in the feature. Yeah, but it's not a super pixel.
Okay. And that FCN is a fully connected network, which goes from the image size to image size.
Yes.
Okay.
I think it's a fully convolutional network, right?
Fully okay. Yes.
Yeah, fully convolutional. Okay. So in our method, the pixel-wise cross-entropy loss and our contrastive loss are complementary to each other. The cross-entropy loss lets segmentation networks learn discriminative pixel features that are meaningful for segmentation. While the contrastive loss helps to regularize the embedding space through exploring global semantic relationships among pixel samples. Finally, we combine the two loss functions as our final training objective. In this figure, we show the learned pixel embeddings by the cross entropy only in the left figure, as well as our loss function in the right figure. We see that the feature space becomes more compact and well separated after introducing the contrastive loss. In addition to the loss design, the discriminating power of the training samples is also crucial for metric learning. Therefore, we aim to mine hard examples to further shape the embedding space. In our case, the gradient of the pixel-wise contrastive loss with respect to each anchor pixel I is given in the equation. Here, Pi denotes the matching probability between a positive or a negative sample with the anchor. So based on the gradient function, we consider negative samples as hard if they are similar to the anchor, and the positive samples as hard if they are dissimilar to the anchor. The similarity is based on is measured based on the dot product between the samples and the anchor pixel. We can also see from the gradient equation that hard examples indeed bring more gradient than the easier samples. In addition to many informative positive and negative samples, we also consider hard example mining for anchors. We treat the pixels with incorrect predictions as hard anchors. This anchor sampling strategy enables our contrastive learning to focus more on the pixels that are hard for classification. This will help to deliver more segmentation-aware embeddings. In addition, we build two memory banks for the method. The first one is the pixel bank. It maintains a queue per category and store pixel embeddings sampled from several latest batches. The second one is the region bank. For each image, we will pull all the embeddings of the pixels in a region and store them in the bank. The two memory banks actually will contribute two kind of pixel contrast. The first one is pixel to pixel contrast, and the second one is pixel to region contrast. Our proposed loss function is very feasible, and it can be incorporated into popular segmentation architectures without any changes to the design. So from the figure, we can see that our model leads to consistent performance improvements over some popular baselines. Okay, now let's see some ablative impairments. This table studies the pixel contrastive learning. We use the HRNet as a baseline. It obtained the MLU score of 78.1. By introducing intra-image contrast, the performance improved by 0.8. Here, intra-image contrast means that we only do contrastive learning in each individual image rather than across different images. After introducing the inter-image contrast, we can see a huge performance improvement by about 2.9. The second table studies the memory mechanism used in the paper. We can see from the second row, even we don't use any external memory bank, or we can say it we use only the current mini batch as the memory. We can obtain a promising improvement about 1.7. After using the pixel memory or region memory, we can obtain further improvements. The table 3 studies the hard example mining mechanism. Here we test three types of hard example mining techniques. The first one is the random sampling, that we randomly sample all the positive and negative samples. The second one is the hardest sampling. That means we only choose the hardest positive and negative samples. The third one is semi-hard example mining. Here we will randomly sample a half number of samples, and then we will select another half number of the hardest pixels. We can see from the table, the random and the hardest mining techniques achieve very similar performance, but the semi-hard techniques can show better performance. In the upper part of the table, we sample the anchors randomly, but in the bottom part of the table, we use the segmentation aware hard example mining techniques. So we can also see that our segmentation aware hard anchor sampling can also improve the performance. Okay, this table compares modern loss functions. Here we consider four losses. The first one is the cross entropy loss. As we have discussed earlier, cross entropy loss is a unary loss. It treats each pixel individually. The second one is AAF loss. This is a pairwise loss. It only considers the relation between each image, each pixel pair. The third one, the fourth one is two high order losses. These two losses will consider all the pixels in a region. So they are high order losses. But all these four losses only focus on local contact learning. Our contrastive loss is a pairwise loss, but it focuses on the global contact learning across different images. So we see that by combining the three losses, AFM and Lewis loss. With the cross entropy loss, the performance improves. And our loss function contributes to the largest gain. In addition, we find that our loss is well complementary with the high order losses and can work with RMI or Lewis loss to further improve the scores. Okay, these tables show the results on 3 popular datasets. Our method shows very promising performance. Okay, finally, I will give some credit to the co-authors. It's mainly from our lab. Okay, thank you for the time.
Thank you for the talk, Tianfei. Are there any questions?
I have a question.
Mm.
And thanks for the talk, Tianfei. My question was, so you show some examples on cityscapes, but cityscapes has a lot of classes, like around 20 to 30 something, right? When you're doing the contrastive learning, do you use some kind of like grouping, like tree, vehicle, road, or do you actually implement the contrastive loss for every class?
Yeah, actually we use the 19 classes for cityscapes. We will do the contrastive learning for each class. But actually we will not use all the pixels for the contrastive learning, so it will not cost too much computation.
And so around how many per image? So for example, if you have a image with 10 classes, you select another image that has those 10 classes, because they should have the same
Yes.
classes, right?
Yeah.
And it's okay.
Yeah, actually we use a memory bank to store the pixels for the classes. So for each class is after some training epochs, the memory bank will be exactly same. So all the classes will share the similar number of the negative samples.
I see. Okay, thank you.
Thank you.
Can I ask a question?
Yeah.
Thank you very much for the great talk, actually. I mean, it's a very ingenious idea, I think, and that's also evident in the results somehow. So thank you very much. And the question is, did you analyze somehow these embeddings? Like how do the clusters are formed if somehow like some pixels get mis-segmented? Do you see them somehow like being between 2 clusters or so? So that would mean that they are sort of uncertain, or could one derive measures of uncertainty from that embedding structure if you put on like a graph structure on those embeddings and so on?
Actually, I didn't fully understand the question, but
sorry, should I reformulate?
yeah, I may know your main idea, but you can say it again.
So the embeddings, you can create a graph structure on that embedding, right? With all the pixels, because some pixels are closer to each other and some pixels are farther away. And some pixels maybe will be in between 2 clusters.
Yeah.
And those pixels might be like half probability it will be a tree, half probability it will be a road or something.
Yeah.
And that should also give some uncertainty measure. Did you look into that?
That's a very good question, but currently we didn't see these examples. Although I think in the semantic segmentation task, at least in cityscapes or ADE such data sets, the cases you mentioned may be coming from the edge pixels. Actually, in the this is this is a good question, and but I think it's still very hard to answer. Maybe we can talk about this later.
Yeah, I would gladly talk about it.
But I didn't make very deep study towards that.
Thank you very much.
Thank you for the question.
Sorry, another kind of technical question. Do you use any data augmentation in these experiments?
Sorry,
are you able to hear me? Hello?
Sorry, I lost the connection. Can you repeat the
Hi.
question?
Yeah, I wanted to ask if you use any data augmentation in these experiments that you showed.
Yes, I use some common data augmentation techniques such as scaling and color gating, or the image cropping, such as like that.
Mm-hmm.
Yeah.
Do you think there is, so if I think about data augmentation and if I change the contrast then have the same labels for these two images, then in a way I am asking those pixels to be near each other in the output space, right?
Yeah.
And your contrastive loss also does that in a way.
Yes.
Do you think there is?
But I think this is different. The from the main insight of our method, we can explain this your question as even if we use data augmentation techniques and we use the cross entropy loss to enforce the pixels coming from two different data augmentation to be the same label, it still use the cross entropy loss, and it can't produce such as a well-structured projection space like this slide. So, but our contrastive learning will explicitly compare the pixels to pixels. No matter they are from the same data augmentation or from different data augmentation or from different images. So I don't think they have some any overlapping.
I see. I understand. Okay. Thank you.
Okay. Thank you.
And if there are no other questions, I think, okay, I would like to thank you again, Tianfei, for the very nice talk and for taking time out for giving the talk. I know you're very busy now with CVPR coming up and so on. But thank you very much, and
Thank you.
see you later.
Thank you for the time. Bye-bye.